As humans seek to extend our lifespan, billions of dollars of research money and investments are at stake. Each separate pathway that we consider therapeutically, interventionally, pharmaceutically, we're betting on a particular model of aging and a particular model of regeneration, rejuvenation, or lifespan extension. But how many of these approaches are actually founded on a proper understanding and model of human aging and lifespan? Today, we're going to be exploring this topic with Dr. Peter Fedichev, a theoretical physicist who has turned his attention on this exact topic. This episode is going to be one of the deepest dives that you will find on the topic of aging, addressing specifics about the difference between the kinds of measurements we make with aging and the actual underlying entropic changes to the cells that actually make up our body. We will be questioning fundamental assumptions from longevity medicine and claims of radical life extension in humans. We will be diving deeply into some rather technical topics. We won't quite get to the point where we're pulling out any math or physics equations, but we will be making reference to some advanced topics. I encourage everybody to stay for the listen. It's a fascinating conversation. And thank you so much for tuning in to the Saving Sapiens podcast. Welcome back to Saving Sapiens. Today, we welcome Dr. Peter Fedichev, a theoretical physicist who is focusing his energy on unraveling the physics that underlies aging and the limitations of human lifespan. Dr. Fedichev, welcome to the podcast.
Well, thank you very much for having me here.
Can you talk to us about why physics is at the root of the kinds of problems that we're trying to fight against when we're trying to extend human lifespan?
Well, the arrogant answer is that, as Mr. Rutherford, one of the great physicists, told once, that all sciences could be separated into physics and stamp collection. So anecdotally, this guy got his Nobel Prize for chemistry, which is an irony here. But jokes aside, I believe that physics is a very powerful science that brought a substantial part of the technologies that have been needed for human progress. And I think that this is still the case. So physics developed ways to treat complex systems. I don't think that it penetrated public discourse like quantum mechanics or general relativity. Not like many people understand what are those sciences, but there are other parts of theoretical physics of the late 20th century where Nobel Prizes were given for phase transitions and other things, where people built the background, the tool set, how to treat complex systems. And I think everyone would agree that biological systems are complex enough. So I think physics still gives some unfair advantage to people who are trying to understand how the most complex things like living systems are working. And my interest in longevity is exactly from that sector.
Can you tell us about the insights that your work has been able to yield, specifically as it relates to the differences in organisms who demonstrate profound and rapid aging and organisms that demonstrate little to no aging? And can you set up for our audience what we understand mathematically when we do use the term aging? When we talk about an organism that demonstrates rapid aging versus one that demonstrates little to no aging, what exactly does that mean?
Well, these are, I think, very interesting questions, because that's exactly what brought me into the field of longevity when, by chance, I was exposed to this discussion. So I think that, physics is a common sense science, so I think I will try to get common sense answers. I think people understand intuitively what aging is, because when we look at people who are aged, we observe that they decline functionally. Now, with proliferation of healthy lifestyles and everything else, I think people are getting diseases later. And that's why we can see better what aging that is separated from diseases mean. And that's, let's say, on a commonly understood level, this is the reduction. I don't know how much people here are familiar with VO2 max, which is a very important characteristic of functional health. This is roughly the amount of oxygen that you can burn in your body. That obviously correlates with the amount of energy that you can spend per unit of time. So this thing is going down to zero, linearly declines with age. And by the way, by extrapolation, it hits zero at 120 years old, roughly. So the point of maximum human lifespan is basically the point when you cannot extract any more energy, really the zero energy point. So this is one example of functional decline, but this is not the only example of functional decline. So we don't need to think that we can move less, but we're still kind of fine. So if you look at cognitive scores, and there are two kinds of cognitive scores that you can measure. Certain things relate to things that you have learned, like the ability to use language. So these things don't deteriorate until very late, until you get some kind of a disease. So for reasonably healthy people, you can still talk and roughly don't understand what you're talking about. So language skills are very strong in people. But at the same time, there are things that are commonly called like fluid intelligence, and this is actually your IQ. And these things also decline linearly as a function of age, and by extrapolation hit zero at about 120 years old. So not surprisingly at the same point. So aging, first of all, is functional decline. So we don't see chess masters at 60, right? So no amount of wisdom actually beats the cognitive ability. So these are the everyday examples of what aging is. Of course, if you decline everywhere, you also decline in your immune function, and that's why you get more susceptible to diseases. That's why people who are aged are dying from COVID more likely. That's why people who are aged are dying from cancer more likely. Some argue that at every point in time we have roughly 1 million cancer cells in our body. This is not a problem for a 20 years old individual, but after another 60 years of decline of your immune function, that immediately becomes a problem for a more aged individual. So to me, there are many definitions of aging, and they work better or less for different animals. But for long-lived species, and believe me, humans are very long-lived species. We complain a lot, but we live considerably longer than you would expect for animals of our MS. We are long-lived species, and for us, aging is mostly the functional decline. And as a consequence of that, we're getting susceptible to diseases. We develop chronic diseases associated with aging, and we suffer in quality of life and die. But if you look at people who are 90 years old or 100 years old, these people are technically disease-free. I mean, they almost do not have bad diseases like diabetes and things like that. At the same time, they are functionally shadows of their former self. So that's the real definition of aging, right? So aging is function, and functional decline is aging. That leads to everything else. Together, that leads to exponential acceleration of chances to die. Our chances to die, because we're becoming more and more fragile, we're less and less functional, we're more and more fragile, our chances to die go up and double every 8 years. Even risks of death from accidents go up every 8 years because of cognitive decline. And that's how it has been. So it was discovered in 1827. So this is a very old discovery. So I think everyone was thinking that this is aging, this is inevitable and everything like that. But then in 2006, there was a paper by Buffenstein, Professor Buffenstein, who now works for Calica, and Calica is the daughter company of Google. And these guys measured chances to die of naked mole rats as a function of their age. And surprise, the chances of death for these animals do not go up, not even exponentially. They just plainly do not go up in any measurable way for more than 40 years, which is for an animal of the size of a mouse is ridiculous. So these guys, in biology, the larger you are, the longer you live. In mammals, this is very easy. Whales live a lot longer than mice. But here you have two animals like mice and naked mole rats that live, that have roughly the same mass. But these guys, one of them apparently doesn't age. This guy has the same probability of death at 1 year of age, at 10 years of age, and at 40 years of age, right? So technically that means that these guys are not aging. And this is not the only example. These guys are mammals, by the way. So I'm not talking about hydras. I'm not talking about primitive. So who am I and who are they? Why should I care? These guys are mammals. Think about bats, for example. So bats are flying mammals. So believe me, these guys are not metabolically compromised. I mean, try to fly and be metabolically compromised. These guys have very high metabolism, and at the same time, they do not want to age. And think about this: this discovery has been just made in 21st century, and it wasn't made by National Institute of. I mean, people in geroscience have been suspecting that, but surprisingly, to get a grant in order to measure the actual aging in these animals, you had to build a company that generates tens of billions of dollars per year in revenue, set up daughter company in Calica, and do the measurement. This is already a very long pitch, but what I'm trying to say here is that even across mammals, there are multiple species. I just mentioned two, mammals and bats, and there are others who refuse aging. Of course, I mean, 40 years, it's a short time. Maybe these guys are eventually aging or something like that. But their rate of aging is zero compared to the animals of the same mass. And to me, that was a very strong indication that, once again, I'm not talking about caloric restriction when you eat less and live a little bit more, right? Here, we have an example in nature that there are mammals that are built from the same hardware as me and you, or at least as mice are built from. And at the same time, these guys fail to age. They don't want to age. And to me and to many people, I think that was a revelation that brings geroscience from theoretical possibility to a phenomenon that you can study and possibly engineer. So at least for me, that was a turning point. And I like that you have brought this example because independent from interpretations of this case, I mean, obviously different scientists may have different explanations why this works. But having such multiple examples across mammalian species in nature, I think this is the strongest indicator that aging is totally plastic. It's at least stoppable. And having such a strong effect in our hands, I think we should actually frame ourselves and actually request your fellow scientists, your scientific friends, to actually focus on this kind of very strong effect, because this is exactly what I think we should achieve technologically in the near future.
So the limitation that appeared to be in place when we would compare something like a hydra to something like a mouse seemed to trap us in a very bad place if we hope to extend human lifespan. Because for the audience members who aren't familiar, the hydra is sometimes described as this almost like an immortal jellyfish, but it does this extreme lifespan trick through a method that is not in any way applicable to human aging, because rather than preserving the adult form, which we're clearly interested in as humans, it essentially de-differentiates. It essentially regresses to a much simpler, earlier life stage. It loses the soma, the traditional body map that it has as an adult, is completely lost, and it essentially would be a little bit like if a person were to regress from their adult stage, shed their body, and start as a zygote all over again. We would perhaps recognize that there's DNA continuity if something like this were to happen, but you and I wouldn't recognize this as being an extension of the lifespan of the adult, with its body, with its memories and experiences and relationships with loved ones. This kind of thing just isn't practical for humans. And then when we get to the kinds of interventions that have been proposed, many of the audience will be familiar with what you mentioned, the calorie restriction models that got a lot of fanfare when they were demonstrated to effectively add a moderate percentage lifespan gain to some of the smaller model organisms like mice, whose reproductive life cycle, of course, would be impacted by a famine. And so they undergo this slight lifespan extension through calorie restriction, something that hasn't panned out well with larger mammals. It hasn't panned out as had been hoped with humans. And then what you've opened sort of for the curiosity here is these mammals that do break the general aging trend. We expect whales, at least in some regard, to live longer because they take longer to reach maturity. The building a body that is larger, and something like an elephant takes time. So there's sort of these expected lifespan trade-offs. But then these two clades, the naked mole rats and many bat species, completely break the body size to lifespan ratio trend that we see in most mammals. You've opened the window to this hypothetical possibility that there may be mechanisms. And the very first thing that we have to wonder is, one, what kind of physics underlies the reasons why they're able to escape the aging? And two, can we actually make progress in identifying mechanisms that would work that might be transferable to humans? And this is kind of, for me, this is my sticking point, because if it's not clinically relevant for humans, if it's an adaptive niche that we don't get any kind of extrapolation from for humans, then what can we learn that we can use for our own lifespan?
Well, of course, my interest here is also purely pragmatic. So for me, the report, the observation of the species was, for me personally, a turning point to switch to biology, because I think when Mother Nature presented us with a demonstration of such a strong effect, I think everyone should be intellectually challenged to figure out how this may work. I was very encouraged to see from our biology friends that if you compare even different bats between each other, and especially bats to naked mole rats, you see that there is more than one way to achieve this, let's call it non-aging, or they call it negligible senescence. I mean, these are just games of words reflecting the fact that we don't know if they age at all or not. But once again, they're aging at such a slow pace, then I would consider them from a pragmatic purposes as non-aging. So this, I think, gives us a very interesting hint. Indeed, it could be that there could be some a very specific adaptation that would be unique to a certain evolutionary history that could not be translated to any other species, and that would be a dead end. That would be just like in nature, you can find an example of almost about everything, but that wouldn't teach anyone anything useful. So I think the most important discovery from the comparative genetics of these species was that all of them have different combinations of adaptations that presumably led to this property, and that I think gives us a chance. This almost close to what is called in physics. In physics, there are I don't know, many people. I think some of you were explained this even in schools. I think in school physics we have enough examples where the same equations explain this other different systems, right? There are multiple examples in physics where you use the same mathematics for very different systems. In physics, it's called universality. So systems that are built from different content, from different matter, organize themselves in such a way that they actually use the same. We can use the same language to describe them. So it appears that aging and non-aging are two universality classes. So very different animals from very different pieces of trees, branches of trees of life, develop either this or that phenotype out of totally different hardware. And this is also very encouraging. That means that essentially every regulatory network can evolve this or that way, depending on their ecological situations, using different signals. Of course, it helps that these things happened in mammals, which are close to us. But the fact that even in mammals you can achieve non-aging in different ways most probably means that we would have multiple options, even for our species. So this is the most inspiring fact here. Of course, if you just compare a naked mole rat to a human, they would be of different size, have different amount of fur, different lengths of average lengths of hyaluronic acid and everything else, because they have to have very hard skin to dig under the ground and everything else. There will be many differences. So of course you cannot decode negligible senescence, non-aging, just by looking at genomes of different species. But if you start believing that this is universality, so there should be some universal properties of bats and naked mole rats versus humans and mice, then you can if you're able to see those universal features that are the same across very different species like bats and naked mole rats, then you start getting guesses. What could that be that differentiates they and us? And then, of course, you can try to backport these adaptations back to mice, for example, because this is even more extreme difference than naked mole rats and humans. And if you can see any results, you can hope that some of them can be also translated to humans. So that's exactly what we're trying to do, because physics is actually a science that developed the language to describe universalities. We're trying to develop language in aging to describe universalities of aging, how to describe aging in apparently unrelated species in the same language, and then try to find biological determinants of the vocabulary of this language in such a way that we could, start doing predictions and doing experiments.
I think part of the challenge with the shared outcome versus the shared mechanism that has become kind of a recurring question for those of us who follow the lifespan research and the aging research is that we have an idea that for these niche clades that have developed very long lifespans, there has to be a certain selection for shared outcomes that we can sometimes express in terms of biomarkers associated with aging, DNA copying fidelity, somatic cell lineage fidelity. There's a few different ways that we can say this species has outcomes that match this long lifespan selection. What's been fascinating to see is the more genomic information we have and the more we unveil the adaptive mechanisms that drive these outcomes in different niches, the combination of features that gets you there for each species has been so different that it makes us almost wonder whether we, even if humans were to say establish an average lifespan of 150 years, what particular drivers that might involve. And for our audience who follows more closely the research in this field, what you may see from time to time in journals like Nature Aging are papers that establish the, say, double strand break DNA repair rates in a long lived species like a bowhead whale, or the tumor suppress the multiplication of tumor suppressor genes in a lineage like the proboscideans. So with elephants, for example, they have around 20 copies of P53. Each separate lineage has this very different approach to either killing off tumors earlier or not letting a tumor arise due to cell communication, like with naked mole rats, or letting a tumor rise and then hunting it down later, or repairing the DNA in advance so that you don't get a tumor in the first place. There's so many different combinations. And it seems like, if anything, this tells us that the type of adaptive suite that might help humans live longer might look nothing like any of these other species.
Yes.
How do we make sense of what to target? And I'm especially interested because you are actually running a company that is seeking to find these geroprotective targets. How do we go from knowing there's this shared outcome through different adaptive traits to then turning that into a target?
Yeah, I like your intuition here, because in fact, this similar outcomes and different mechanisms is an archetypical property of complex systems. You can see it everywhere. You look, for example, at coevolution of electric cars, and they start looking the same,
Mm-hmm,
although they're
mm-hmm,
built from different components. And even nuclear powered and diesel submarines more or less look like whales and things like that. So whenever you see competitive environments and complex self-organized systems, they like to develop common properties. But once you
mm-hmm.
open such systems, you end up having totally different mechanisms, right? So This is exactly this. This is related, let's say, on a more philosophical side, to this complex of concept of emergence, when more is different. When you go from micro scale to macro scale, suddenly things self-organize and start developing properties that you don't expect from the individual constituents. And at the same time, as Taleb is saying, less is more. So less and less properties become important, right? So there is a growing disconnect. The more complex is the system, the more is the disconnect between the ways the system is organized and the outcomes that the system is demonstrating. Complex systems like to hide the causes, as we know, in a very hard way in medicine. So to respond directly to your question is that, at least, I mean, unless we don't have a strong drug against aging, whatever I'm saying is a speculation, but I can share my beliefs here in response to your question. So my beliefs are such that you cannot build these things ground up. We have, I don't know, 300 theories of aging. Everyone knows their particular, best mechanisms that explains aging. But when you have so many explanations, most probably means that none of these explanations is fundamental, right? So this is exactly this many mechanisms, the same outcomes situation. I believe that in order to understand how to make humans more long-lived, we should study humans. So we should study real-world data from aging humans. We live in the best of times right now. More than 500 million people worldwide have their medical records digitized. So it's like in the airspace industry. When an airplane crashes, everyone knows the whole picture, and then the every finding is getting reintegrated into flight manuals. So we're approaching the same now in humans. So for the last million years, people were dying in vain, but now we have people who are dying with full medical records. They are genotyped. We have more and more information on them. So we're understanding better and better why these people developed diseases and eventually died. And we understand how this is related to their genetic compositions. And we see that within our species. So if you are able to develop models that can be applied at the same time to naked mole rats, to mice, and to humans, I mean, really, literally the same models that speak the same language, where you see which properties of these species are actually responsible for slow aging. And when you can measure this property in humans from human data and associate genes to that property, you start doing generalizations, right? So you see that there is a certain property in naked mole rats that presumably controls their long lifespan, and humans do have the same property, and I can actually provide examples. And then this property is at least partly genetically controlled. Then you immediately start generating ideas what you want to do in humans. So the short answer to your question is that we should employ this property of complex systems, which is universality. We should be able to use the same language across multiple species, but apply these models for humans specifically and try to find which genetic factors control those properties specifically in humans. And that, to me, is the shortest way to actual therapeutics. I don't really need to know how precisely naked mole rats generate their super abilities. I need to understand which properties of naked mole rats that are measurable in humans are responsible for those super abilities. And if that property is measurable in millions of people with genotypes, I want to see which genes are controlling that property in humans, because that's precisely what I want to do therapeutically. And this is the promise and the power of real world data together with modern machine learning. We can actually study aging in humans from human data and try to generate ideas how to cure humans. That's precisely what we're doing. I hope that was at least
So
partial.
for members of the audience who are interested in this for personal reasons, for members of the audience who are funders and founders who are investing in the myriad of startups that are attempting to and claiming to offer these sort of nature inspired copies of mechanisms that we are finding in other species, for science communicators and doctors who are telling people that they should go read about the particular metabolic pathway that's upregulated in a naked mole rat to increase their DNA copying fidelity. You're making a point that is so critical and so important here, because the way that complex systems select for shared outcomes does not imply that the components of that system are the same. And to give the audience a visual example, if you can envision how similar the streamlining of the body shape of a dolphin and a shark are, you can hardly think of two organisms that are more distantly related. A shark and a dolphin aren't, the one is a mammal and one is a has never been out of the ocean, and they're, if you open up their internal anatomy, they're wildly different. If you look at their brains, they are wildly different. uh, they're about as different ancestrally as you can get, yet the final sort of optimized streamlining of a shark and a dolphin are so similar because these complex systems are being selected for optimization under similar constraints. And Dr. Fedishev, when you talk about how the kinds of aging outcomes for very long lifespan can have similar outcomes but through different mechanisms, this idea that we should then go look for the mechanism that would accomplish that outcome in humans rather than trying to transpose that particular metabolic pathway or that particular enzyme or that particular specific naked mole rat gene variant into a human, is it's an informed view of lifespan extension that I think is unfortunately missing from a lot of the conversations on longevity. And you also are one of the few voices, I think, who specifically recognizes that for these complex systems, you need the modeling to scale at the level of machine learning. Because one of the really severe weaknesses in the single target therapeutic development pipeline in classical pharmacology is that we look for single targets for a single drug to act on in a simple, easily described mechanism. The classic, is somebody has a trait, and we, inhibit one receptor through one particular drug, and we hope that by inhibiting that receptor we shift some physiological balance back, whether this is a blood pressure medication or any of the sort of classical drug classes. Why does that single target, old school, pick a receptor and block it approach not work for lifespan extension?
Well, I would maybe rhetorically try to counter argue here, but I hope to provide an interesting point. So, in a sense, as you may know, certain diseases take a substantial part of human life. So, for example, early diabetes takes out 6 years of life, meaning that if tomorrow somebody would produce a perfect drug against diabetes, that would essentially switch it off, which is not yet achieved, but we are making progress. Then you could add for those sick people 6 years of life, then maybe on average in the population you would achieve a few years of life extension on average. And as you may know, we have now these GLP-1 receptor agonists, and these guys are reducing risks of multiple diseases other than diabetes and obesity, not Alzheimer's disease, by the way, as we have just learned out a few weeks ago. But I think it's safe to say that on a population level, by hitting a single receptor, you can still increase life by a few years, right? So it's always a matter of scale. I think
Well, if I can clarify though, just for the audience, because this is a common equivocation that happens even among many of the physicians who are participating in the sort of longevity medicine movement, is there's frequently an equivocation between maximizing the health span or increasing the average life expectancy of your patient population. I want to be really clear. This is different than when we talk about increasing the lifespan of a species, right? When we
exactly.
talk about and I'll give a dramatic example from nature, because I think this really is probably my favorite example of this. When you hatch as a sea turtle, your life expectancy is shockingly short. Most sea turtles that hatch are going to be eaten somewhere along the path to just getting to the ocean, or swimming about in the ocean when they're only a few inches across makes them prime prey species for just a lot of different sharks and large fish and things like that. There's a very, 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 very small chance of reaching the full size, like a leatherback sea turtle. That it has a very small chance. And so the average life expectancy for a sea turtle at hatching is very, very low. And I know you're familiar with the mathematics behind population averages, but when we talk about the biological lifespan of a sea turtle, we're talking about the actual upper limit to the lifespan of an organism that does successfully pass that juvenile mortality stage. And similarly with humans, we many of us in the population, especially in areas impacted by chronic diseases, we have both a reduction in our life expectancy, and we often have a reduction in health span, right? Like, even though we may live into our 80s, there's often kind of these late chronic illness periods. But the upper limit that you've spoken about, that 120-year functional decline past which essentially no human has ever lived, that kind of extension past that upper limit of lifespan,
Yeah.
it really, truly, we have no reason biologically, mathematically, from physics, from population genetics, we have no reason to think that there's ever a single target that would push us past that.
I like that you pick the ball, because I think now together we can make this rhetorical exercise complete. So essentially, what I think comes out from this exchange, that if we have a very particular failure and a very specific mechanism, something that leads to lipid metabolism, for example, or maybe to diabetes, then since this is a mechanism that is broken, we can go and try to fix it. And for such situations, going single target sometimes work, right? We know that
Mhm.
drugs can cure specific form of cancers. So there are multiple examples then where a specific system fails, you can actually you can revert the failure by going mechanism based to a very particular point, to the weakest point with a targeted drug, and actually produce a lot of effect. And at the same time, I think what comes here also from your comment is that intuitively we understand that aging is something else. So aging,
Exactly.
yeah, and here maybe it's a good idea to actually reflect why do we have that linear decline, and how much is it different from getting diabetes, for example, because even diabetes takes some number of years of life, and of course, if you get rid of it, you can live longer. So what actually happens is that, of course, we have these huge systems like immune system, different components of metabolic systems that if fail, that produce very substantial decrease in quality of life, and these are the targets of standard disease-based, disease-focused medicine. At the same time, we are very complex machines, and sometimes we have very complex systems that are working in sequences uh, with each other. And sometimes they fail, like one molecule is not there in the right time. Something is not fixed, and then it's get compacted into chromatin, hidden from any possible repair mechanism, and then you have one error more in just one cell, and then in another cell you are now one error more in a totally different place. You have some protein that cannot be misfolded, and it sits in your cell, and a different mechanism sits in your another cell. So every time, whenever you have a bunch of metabolic steps across 1 trillion cells in your body, these kind of benign mistakes actually end up fixed in your DNA, in your proteome, somewhere in your membrane. Each of that thing is totally benign. I mean, the effect of each of those things on your health is nothing. You don't have ICD-10 code for that particular error anywhere, right? But the total number of such errors that could happen in every cell is huge. It's astronomical, because the number of particles in your cells, and also you have 1 trillion cells. So think how many combinations of those errors can show up. There will be no two humans that have the same number of errors in their body. I mean, the same number, yes, but the same pattern of errors. in their body. So essentially, every person is different from another person. Every cell in your body is different from another cell in terms of patterns of those errors that accumulate. So the only thing that you can tell, the only fact that you can formulate about these people is that total number of these errors is going linearly with time. I mean, the more you live, the more errors you accumulate. But the exact patterns of those errors are very, very different across cells, across humans. Each of us becomes exponentially more different from each other as we age. And then if you think about it as a control problem, of course, in order to fix it, you have to come with diagnostics, right? So you have to diagnose every cell to figure out that in this cell you have this issue, in this cell you have this issue. And not to mention that you have to invent infinite number of ICD-10 codes, but you also have to invent infinite number of drugs, regulate them, go through clinical trials. But even if that would be possible, even if we could fix any error in every cell, still you would have to find with drug A to one cell and with drug B to the other cell, which is totally beyond any our technological ability. We are coming with the same drug to every cells, unless some cells do not get drug in, like brains somehow. What I'm trying to say is that the pattern of damage, not only the amount of damage is a problem, right? The more damage you have, the lesser is your quality of life. That's okay. But also the pattern of damage is so sophisticated that, let's say, with the technologies that we're having with these 10 to 15 years from now, we are not able to repair this damage because the pattern of damage is so different in so much different cells that we don't have enough control on the molecular level and enough diagnostics to ever apply such interventions, if they were available, to an extent to repair this ultra complex pattern of damage. So that's why what I think that's where the conversation is actually coming out. I think coming down to is that I think people intuitively believe that we can kind of take out damage from our body and be younger and live longer. What I'm trying to say is that the damage is sticking in such complex patterns that we cannot eliminate that damage. We can only prevent damage to accumulate. And that's to my taste is the explanation why it's very hard to actually break the maximum human lifespan, right? Because the damage is so different that it's hard to think that you can come with a single drug that would suddenly affect all sources of damage at the same time. So that to me maybe explains why we see mammals that are aging slowly, but we do not see mammals as hydras who are getting back in time. So what I think that brings to the table is this idea that it's not like damage is very dangerous or the damage is very hard to understand, but the pattern at which the damage shows up is so complex that it's hard to unwire. That's the only kind of technological possibility that we may have is try to reduce the rate at which the damage is accumulated, that this may be possible, pairing damage with the technology that we have. Most probably this means that in the very near future, we should acquire technologies that will slow down damage. That's how these animals are presumably not aging. But we are not going to acquire technologies that would repair this damage, meaning that rejuvenation is hard, but slowing aging is possible.
Kind of clarity is incredibly important, both for patients and consumers who are considering investing substantial amounts of money in promised interventions and rejuvenation therapies and things that they perceive will somehow remove the aging associated damage and this sort of very highly distributed increase in entropy that is happening throughout the body. And I think biologically, there's a really important lesson to be learned when we think about the fact that bacteria have successfully replicated for the entire duration of our planet's history. They're undergoing a constant lineage specific selection where if a cell lineage accumulates an unacceptable amount of damage, if a daughter cell splits into two cells and one of them is carrying a mutation that's too severely functionally impairing, that lineage stops having offspring, and the lineage that has that does not have the damage keeps on replicating. And anytime there is some novel environmental damage done to one particular branch of a bacterial lineage, it results in trimming that cell line out of survival. And when we see a hydra get injured and it reverts back to an earlier de-differentiated ancestral stage, it is also recognizing that that cell lineage is too damaged to keep going and abandoning it. And I think the sort of theoretical difference between the two is something we often ignore, but it is the foundation of the irreversibility of aging in humans, because the any particular thing you want to talk about, whether it's the accumulation of metabolic waste in certain cells, whether it is acquired disruption of chromatin packing, which with your DNA that starts off nicely, nicely wound around histones and nicely packed away, and over time it's just stochastically disrupted through interactions with the environment, through random somatic mutations. The fact that you are a living organism made up of trillions of cells, and each one of those needs to continue to have healthy daughter cells, but eventually that those daughter cells are going to take on damage. We don't have an equivalence to a single target disease. If you are born, even nowadays, if you are born with certain types of, single nucleotide polymorphisms, there are some diseases that we can either reverse or, as treat that particular protein deficiency or block a particular problematic peptide for the duration of your life. And that single target, like you mentioned earlier, can be addressed. This is not that. This is you having multiple, dozens and dozens of different types of tissues and cell lines that each need to continue propagating. And we don't have the privilege of simply being able to abandon a cell lineage because there was too much somatic damage along the way. Why do you think this has not become standard knowledge in the longevity space? Like, is it resistance to this because it's a sad recognition? Is it this is a hard problem, we don't want to face how hard it is? Is it to do with the industry needing single targets, or is this just conceptually missing from the training people get in medicine? What do you think drives that?
Well, I think it's a combination of these factors. As you may know, in the end of 19th century, that was a hot topic in physics. There were people knowing about second law of thermodynamics, knowing that most complex systems are developing irreversibly. I mean, that was empirical experience. And at the same time, people were started thinking about atoms, and they knew that atoms follow the laws of mechanics, and the laws of mechanics are reversible. And as you know, Boltzmann killed himself because he could not convince academic community that in the world of colliding atoms, the entropy may change only one way. I mean, that was a personal tragedy, and that was a very important development in physics. So I think biology now lives conceptually in the end of the 19th century, because in biology you have very good control on the molecular level now, right? I mean, look at these papers in biology with these genetics, with single cell omics. These people actually can see how molecules move and interact with each other. So they live, I think, under the framework that if I do this and it goes one way, I will stop doing that and it will go the other way. So they live in the universe that is full of reversible processes. What I think doesn't occur to people that if you combine enough reversible processes together, and 1 trillion cells is more than enough, believe me, then what appears to be reversible stops behaving as a reversible thing. But this requires an intellectual jump in a way. This is a quantum leap, right? So they have so much control on microscopic level that they don't understand that as a whole, this system starts resisting control. So I think that if you go to a layman on the street, I think most people would intuitively think that aging is not as reversible as many try to say. So I think common sense is telling that reversibility is limited, but this technological um, might of modern molecular biology, I think, prevents people from thinking that the control is limited. And then, of course, I think this idea of reversible damage proliferates in the field. Obviously, I think there are ideas of these hallmarks of aging, the idea of repair, the idea of seeding, I don't know, 5 companies against any hallmark of aging that together should bring us infinite life. I think this is very intuitive, and this is a situation where people want to believe, right? I mean, it's Boltzmann had to kill himself, not the guys who were propagating the idea of microscopic reversibility. It's a very hard pillow to swallow because in the world of technological super abilities, any idea that nature may limit our abilities to control systems is against kind of humanitarian drive, I would say, the civilizational drive. So I think it's very countercultural on many levels. And that's where I think, once again, physics is powerful, because in physics we have already killed our Boltzmann. So we are a little bit wiser here. Biology, to my taste, hasn't yet killed their own Boltzmann, and this is being aging is precisely the problem when biology has to come to term with microscopic reversibility.
And if I can speak to the audience for a second to try to really for any listeners who live in the biology world that Dr. Fedichev is describing, where you're zoomed in on this one molecular mechanism and you see that this is a reversible mechanism and you can map it out, but then it doesn't make sense that it's not all reversible at scale organism wide. If you can imagine kind of where with Boltzmann and statistical thermodynamics, the kind of bridge to get there is you can essentially imagine if you can imagine a box with one ball bouncing around that box, it has an equal probability, if it bounces at random, of ending up anywhere inside that box. And we can all understand that that is a reversible thing. If it ends up in a corner here or halfway across the box down there, that sort of, Pac-Man ping pong ball thing bouncing around is easy to imagine on a reversible path. But the moment you scale that up and you have 10 trillion balls bouncing around in a box, the chance, if we start them all off in one tiny little corner and we all let them randomly bounce around, the chance that they all randomly bounce around and end up back in some tiny little packed configuration in the corner, we all intuitively understand this principle in statistical thermodynamics, that configuration, that starting configuration of all the balls crammed into one corner of the box, really truly is never going to go back to that state. There is a nearly as close to a zero probability of that configuration ever being attained again. It just isn't going to happen unless you go back to your original setting and you start the box off and you start them all packed in like that. We're facing that same sort of statistical problem with organisms when we start them off with a single cell, with optimized chromatin packing, with properly, a properly methylated genome, with all of the mitochondria in order and all of the gradients around the cell exactly as they need to be. We can totally understand that that's how the system needs to be. But when you multiply this out a trillion fold across all of these cells that are all dividing and all accumulating damage, the chance that we can all get all the balls back in the corner all at the same time, there simply isn't a way of actually doing that. We don't have a drug. We don't have a target. We're not waiting to flip a switch in the genome that is magically going to do that, because the statistics on that, they just don't work. This is what physicists came to recognize back with Boltzmann, and to this day, it doesn't matter how efficient an engine is. It doesn't matter what kind of system dynamics we're looking at. Nobody has cracked it in physics, and biology is an even messier system. I hope that someone in the audience who's throwing millions of dollars at the next single target therapy will at least be honest that it is okay and it is acceptable to target aging associated diseases that have single targets. That's a great idea. But if you're promising people, and you and I know some of the big names in the aging world, there have been a few who have said we're on the brink of this runaway lifespan extension where humans will be living 1,000 years or more. That is not something that has been conquered yet. So where do we go from here?
Well, I'd like to be still optimistic because, once again, physics is science that I think triggered the technological revolution, and quite a lot of things became possible, even though none of them goes against the second law of thermodynamics. What I'm trying to say that the world where we are not fighting with the second law is still a good world to live in. Jokes aside, I believe that still you can go with single target therapeutics that would eventually breach the average lifespan to the maximum lifespan. So our current average lifespan is 80 years old, and you can do better than that. You can bring everyone to 120 years old
Agreed. Yep.
with single target therapeutics, and this is an effect size which is order of magnitude more than anything that you can realistically ascribe to Ozempic or something like that. So as you know that even Ozempic that maybe extends life on average, with all the caveats that were discussed, by 1 year, was still $500 billion company. Eli Lilly with a better Ozempic is now approaching $1 trillion. So maybe a drug that would extend life by 10, 15, I don't know, 20, maybe 40, but 10 to 20 years will be a massive technology that will change the world. Of course, we understand that this technology will extend life, but will not arrest the functional decline.
Mm-hmm.
So in a way, this is exactly the future that everyone is afraid of, that we will be definitely living longer, but increasingly in a state of worse function. I'm sorry about that, but even that would be a huge advantage, because if that would on average give people another 10 plus years of life, we will see maybe another general relativity, another $10 trillion company or something like that. I think there is a very non-linear effect on keeping top performers in human population longer alive. And this is like very technically possible with the technologies that we already have. That's what we're working on, and maybe some other people, maybe not, I hope not, but us or somebody else will achieve that. At the same time, as we know, the entropy cannot be reduced, but the entropy production can be slowed down. What I still believe we can do, not to rejuvenate. I mean, we can rejuvenate a little bit, but let's put that aside. What I'm saying is that as I'm watching this negligible senescent non-aging animals, we should be able to put a brake on the rate of aging, and that will produce even larger life extension. So my personal forecast is that the geroscience dream is on. It's not in repair, but it's on bridging the average lifespan to the maximum. That's something that somebody will do, hopefully in 10 years. That will give people another 10 years. So having zero aging rate is not totally unrealistic. The only problem is that if we can make that persistent. So to make it persistent, that would require another level of technology that I can only speculate about. I don't know how to translate it, how to do clinical trials and everything else. But 10 years is a long time. So I hope that within 10 years, somebody will at least propose something that would change human maximum lifespan. And this is not impossible, as I said. You cannot rejuvenate, but you can stop aging, and that's something that people should be focused on. What I'm just trying to say is that forget about small effects. I mean, everyone can do diet, caloric restriction, and everything else. We should frame our development work and scientific work on understanding what aging is, how multiple causes can bring the same results, what are the levers of longevity in humans, better from the data, because that increases chances of successful clinical trials. Make sure that whichever dollar you spend is spent for high effect sizes, at least theoretically, because then on average at least somebody will achieve that. And yes, don't understand me pessimistically. I mean, physics is the law and everything else is a recommendation, as Elon Musk is saying. So you don't need to fight physics. You need to start loving physics and trying to understand the physical constraints of the world you're living in. And all modern technologies are actually within the physical constraints. So this is not a technology poor world. So by, I think, making friends with physics, biology will eventually understand even better the power of its science and actually bring therapeutics with effect sizes much better than one year of lifespan.
So, in the distant future, if you see an adult living to be 119 years old, they're able to function just until the very last moment. Can you tell us, do you see that person being on a suite of single target therapeutics that just happen to mitigate the age associated disease risk, sort of divide and conquer method? Or are you envisioning the holy grail geroprotective
I
one
believe,
pill?
yeah, once again, this is a statement of belief. So I believe in universality, right? I don't like the idea of personalized medicine too much. I don't like the idea of a cocktail of a trillion drugs successfully passing clinical trials and everything else for two patients in the population. What I believe is that there is universal biology or physics that controls, as I said, the difference between 80 and 120 years old. This is like totally concurrable with the current technology, with the current data. This will be achieved. As I said, this is not exactly the win over aging, but this is a huge win over lifespan. Actually, I'd say my recommendation is actually strange. So if we are talking about functional decline that actually kills us and defines our maximum lifespan, the only way to, I mean, personally, within the current means, to control your personal maximum lifespan is actually to reach as higher physical and mental capacity as you can, as young as you can, because that gives you the height from which you would go down, and that would define your final point. What happens now is that we're not living until the maximum lifespan. We are dying at the average lifespan. So I envision, let's say, the longevity version 0.1, where our youngsters are actually encouraged to reach the maximum physical and cognitive and whichever else capacity in the ways that society would help them to achieve at their 30s, so that they will have more runway at the current rate of aging. And then they would be under a drug or a vaccine that would push all the age-related diseases till the very last point. And that would be both like institutional and pharmacologically meaningful way to extend functional span, which is the most important thing. But this is a combination of the two. You have to have the height.
If you're going to have a functional decline, then at least raise the curve by maximizing biological function or neurological function earlier. But to be clear, though, you actually are promoting the idea that there might be a single geroprotective agent.
Yes, that would bring 80 years to 120. Okay, maybe 80 years to 100 at first, but yes, I believe. So once again, this will not intercept the decline, right? So I'm
Right,
really,
right, right. Yeah, the slope of the
this is
curve
not
isn't.
truly aging. This is not a truly aging track, but this
Mhm.
will square the curve till like, you can argue that this is actually happening right now because of the societal engineering and everything else. It appears that our maximum lifespan is not changing because there is no single drug interaction.
Yeah, this is a health span optimization pitch.
Yes, but what I'm saying that you can do ultimate health span optimization with a traditional single target, single drug fits most, not all, but most people. And that would be on a societal level a huge thing that is totally achievable and is within our hands if we want to do it. But with functional decline, as I said, and we discussed, this is a totally different thing. Once again, I don't believe it's impossible. What I'm saying that few people are doing that. So organ tissue replacement, regeneration. I mean, these are the keywords you should be watching there, right? We have now increasing number of companies that are trying to do ex vivo regeneration, for example, for aged patients. So these are very nascent, but these are, I think, kind of predecessors of ancestors of future technologies that will eventually extend maximum lifespan. You ask me how I see the future. That's what I'm telling you. I believe that 80 will become 120 with technologies. I mean, 80 will become maybe 100 at first, but eventually 120 with the technologies that are totally within our grasp and which physics can actually help people to channel their resources to achieve it faster. That's not precisely our dream, but that's still a huge thing to happen, right? So for those who want to prepare themselves to the world where these technologies show up, think about your personal runway by increasing your functional capacity at whichever age you are right now. Believe me, this will never hurt. And I believe that there are people right now who are thinking about the next level of longevity tech that will extend human maximal lifespan by reducing the rate of functional decline.
I will wrap my questions up just with a tiny bit of, we'll say, either clinical insight or clinical skepticism. I'm not sure what the defense would be for a single target geroprotective agent, because what every candidate has shown for every therapeutic intervention that has tried to kind of play this role, I haven't seen a candidate that would even remotely
I
approach
can,
this to be
uh,
realistically described. But beyond that, my argument isn't even just that it hasn't happened yet. The problem with advancing the sort of single switch argument is that it represents a claim about the evolution of polygenic traits and pleiotropic systems where there are these sort of single switch events. And I think from biology, we have extremely overwhelming evidence that every somatic cell lineage accumulates mutations. We have 100% confidence that there aren't any species where these single switch targets extend lifespan beyond what the clade has been demonstrated to achieve. And when you do have the tolerable lifespan extension in the very long lived clades,
mhm.
it is never single switch. This has been kind of the most fascinating part of seeing the like bowhead whale genome and the naked mole rats, that whenever you see it in the case of naked mole rats, for example, they have multiple completely separate adaptations to tolerance
if,
of
if
anoxic
you,
conditions and control of mutation rates. And it's always multiple variables. What would that even look like?
First of all, you don't know. I mean, I don't know if I'm right, right? So you must be skeptical like this. What I'm trying to argue is that, I mean, we think about ourselves as a bad agers. In fact, we are already super optimized. We are long-lived mammals already. We are super resilient for our MS. And what I'm trying to say is that the evolution actually has done most of the work. So yes, I
Mm-hmm.
agree.
Yes. Agreed.
I agree that you have to have multiple adaptations to, I mean, if you start from mice, you have to do multiple adaptations in order to become naked mole rats. What
Mm-hmm.
I think at least our data analysis is showing that humans have done most of them already.
Mm-hmm.
We are a lot closer to naked mole rats data-wise than mice. So that's why I think we need to tilt a little bit, right? That's my point. That the most crucial adaptations that I would never attempt with currently available biotechnology already done. We are when we're young, we look a lot more like negligible like non-aging species than mice, and
Right.
that's to me is crucial. The most of the job has been already done by evolution. We are just a little bit under naked mode rat.
Agree.
That gives me hope.
We're like one variable away from doing that. Is that kind of the pitch?
Well, order of one major change remaining. So, well, maybe we will not achieve exactly non-aging, but if we do it right, I believe that with one adaptation, once again, there are multiple adaptations between mice and naked mole rats.
Mm-hmm.
Those which I don't know how to do with modern biotechnology are already made, where most of this pleiotropy sits.
Mm-hmm. We can all
That's
be
hope.
hopeful that that is the case, and I would certainly love to be
I mean, that's why I'm here,
convinced that
because
that is achievable.
I know your arguments, and of course I changed myself. But I mean, when all this picture kind of materialized in front of my eyes, of course I got depressed, right? Because I entered the field from the direction of reversibility of aging, right? Because this
Right.
is like a rallying cry in the field right now. So when these things got revealed, let's say to me in sufficient data, actually, you may know there is. Do you know a story about Streller, the guy who is Streller Milton paper, one of the best theories of aging in 1960s? So the guy actually figured out what aging is in humans pretty well. He published a science paper, and then this guy realized that aging in humans is mostly entropic, and he gave up.
Mm-hmm.
He started thinking about mind uploading and other things, and he totally switched the field. He stopped doing biology of aging. So
Hmm.
I think this is a very depressing moment in the life story of every good longevity scientist, because you have to understand that aging is entropic. But then the difference is what the conclusion you're going to make. I think Dr. Streller didn't see naked mole rat. If in 60s they saw naked mole rat, I think together with another bunch of guys, we would have a solution right now. So we should not underestimate the power of culture here. It's like with GLP-1s, before obesity was a disease, we didn't have a drug against obesity. So it's very important what we are framing for ourselves. So, for example, when Streller was active, second law was respected. When he understood that aging is entropy, he stopped. But now we're in a much better position. We know that aging is entropy, but we have animals that almost do not age. And that's a much better situation to keep on thinking about this problem.
I agree, but we know very thoroughly that it's through a whole host of different mechanisms. With radical lifespan extension in even shorter lived organisms like Drosophila, we can achieve radical lifespan extension, but it's through changes at sometimes hundreds of different loci throughout the genome. And I think
And,
that's why we should
I
always
gave you,
remain skeptical that it'll be a single target.
I gave you a very specific, I think, prediction here is that I think that humans are already engineered for extreme longevity. Yes, the maximal lifespan appears to be fixed, and this is our empirical, I think, knowledge from the last 200 years. But still, the average lifespan is somewhere written in our genome, as well as the maximal lifespan. And the maximal lifespan is written in a very obfuscated manner. That's why it's very technologically challenging to change. And what I'm trying to tell you is that the average lifespan is written almost like in plain sight.
Yep. Yep. Very, very informative discussion. Thank you so much, Dr. Fedichev, for joining us and shining some math and some physics light on lifespan and aging.
Well, thank you very much for your questions. Always a pleasure to have intelligent conversation.
Thank you so much.